That's how we discovered dark energy, at least, that's how the story begins. An extraordinary event sent shockwaves through both the astrophysics and particle physics communities. A sudden, intense burst of high-energy neutrinos recorded at CERN coincided almost perfectly with an anomalous transmission from NASA's Voyager 1 probe. One signal emerged from beneath the Earth's surface, from the world's most powerful particle accelerator. The other traveled billions of miles across interstellar space. That they occurred nearly simultaneously, within half a millisecond, was either a cosmic fluke or the sign of a hidden link between the quantum world and macroscopic systems. Was this synchronicity purely random, or were we seeing the first evidence of an undiscovered thread weaving subatomic events with deep space instrumentation? What follows is a journey through experimental techniques, theoretical frontiers, and the farthest reaches of our imagination as science attempts to answer that question. On March 22, 2025, CERN's neutrino monitoring systems lit up with activity. A powerful burst, lasting just 3.7 seconds, registered across detectors at the Large Hadron Collider and Italy's Gran Sasso laboratory. Unlike the smooth energy curves from cosmic ray neutrinos or solar activity, this signal was sharp and distinct, with a pronounced peak around 2 tera-electronvolts. The sheer number of interactions, over 120 within seconds, was unprecedented. High-speed GPS sync clocks confirmed the time. 3 hours 14 minutes and 7 seconds Coordinated Universal Time. Yet, while scientists at CERN were still reeling from the data, NASA's Deep Space Network reported a strange modulation in Voyager 1's carrier wave, recorded at the exact same time. Considering the spacecraft's radio signal takes nearly 20 hours to reach Earth, the implication wasn't that the burst caused the transmission or vice versa, but rather that both originated from a shared event or mechanism, one capable of spanning astronomical distances and scales simultaneously. Theoretical models sprang up like wildfire. Some proposed quantum entanglement, suggesting Voyager 1's electronic subsystems were somehow entangled with particle interactions at CERN. In this interpretation, changes in one system would be mirrored in the other, not through signal transmission but through fundamental quantum correlations. Others speculated about sterile neutrinos, hypothetical particles that could interact with both known neutrinos and electronics via a dark sector field. If Voyager 1 passed through a region rich in such particles, it might have briefly experienced interference, just as CERN's neutrino burst unfolded. A more conservative school of thought suggested a powerful astrophysical event, like a magnetar flare or quasar jet, simultaneously emitting neutrinos in a low-frequency field that disrupted the spacecraft's radio systems. Yet, no gamma-ray or X-ray observatories reported any such event at that time, leaving theorists grasping for less visible culprits, such as off-axis or silent cosmic explosions. As excitement grew, major neutrino observatories across the world joined the investigation. IceCube in Antarctica combed through archival data for similar spikes. KM3 deep beneath the Mediterranean Sea, began scanning for directional correlations. Japan's Super Kamiokande reanalyzed historical data for temporal alignments with deep space transmissions. All eyes were on whether other spacecraft had exhibited anomalies at the same time. To streamline global response, scientists proposed NeutrinoNet, a planetary alert system that would function like an earthquake early warning network, allowing detectors and space agencies to compare data in real time. If even a handful of neutrino events can be linked to space probe disturbances, it could indicate a fundamental coupling, some hidden principle of nature that bridges quantum fields and engineered systems across the cosmos. The implications are staggering. If this connection is genuine, it would suggest that our universe allows information to propagate or correlate in ways that defy our current understanding of causality and locality. Quantum gravity, entangled electronics, even holographic principles from string theory have been proposed to explain how a spacecraft billions of miles away could respond to an event on Earth. Engineers are already considering how such interactions might affect future space probes. Could shielding or design reduce susceptibility to neutrino-induced disruptions? More provocatively, could quantum coupling enable faster-than-light communication? The Voyager CERN anomaly may be just the first clue. If repeated and verified, we may be standing at the threshold of a deeper reality. One where information flows not just through space and time, but through a fabric far stranger and more interconnected than we ever imagined.